Hello everyone and welcome back to my channel where we discuss all things related to networking. This is part 2 of our IP addressing series. In part 1 we covered the fundamentals of IP addressing. Now, it's time to dive deeper into the world of IPv4 frames, ARP, private and public addresses, subnetting, and CIDR notation. And hey, if you're hungry for more networking knowledge, don't forget our blog. We publish in-depth articles, tutorials, and resources to help stay on top of the latest advancement in this ever-evolving field. So if you're ready, let's get started. At its core, an IPv4 packet serves as a vessel for transporting data across different networks. It encapsulates data into discrete units called packets, allowing for efficient and reliable transmission. Each IPv4 packet consists of a header and a payload. The header contains essential information about the packet, while the payload carries the actual data being transmitted. It consists of various header fields that provide essential information for proper routing and delivery of data. Let's explore each of these header fields in detail. The version field specifies the version of the Internet protocol being used. In the case of IPv4, this field holds the value 4, indicating that the packet is compliant with the IPv4 protocol. IHL stands for Internet Header Length. It indicates the length of the IPv4 header in 32-bit words. Since the header structure may vary due to the presence of optional fields, this field allows the receiver to determine the exact length of the header and locate the beginning of the payload. The type of service field, also known as the differentiated services code point, enables the classification and prioritization of packets based on specific requirements. It allows network administrators to assign different levels of service to packets, ensuring efficient delivery based on factors such as packet priority, delay, throughput, and reliability. The total length field indicates the total size of the IPv4 packet, including the header and payload, in bytes. It enables the receiving device to allocate sufficient memory to accommodate the entire packet. The identification field assigns a unique identifier to each packet generated by the source device. This identifier aids in reassembling fragmented packets at the destination, ensuring the correct ordering of the original data. The flags field consists of 3 bits used to control the fragmentation process. These bits include the reserved bit, the don't fragment (DF) bit, and the more fragments (MF) bit. The DF bit, when set to 1, instructs routers not to fragment the packet, while the MF bit indicates whether the packet is part of a fragmented sequence. In cases where a packet exceeds the maximum transmission size of a network, it may be fragmented into smaller units. The fragment offset field specifies the position of each fragmented packet within the original data stream, enabling the destination device to reassemble them correctly. The time to live field indicates the maximum number of hops, or routers, that a packet can pass through before it is discarded. Each router decrements the TTL value by 1, allowing for the detection of routing loops and preventing packets from circulating indefinitely. The protocol field denotes the type of data carried in the payload of the IPv4 packet. It specifies the higher-level protocol to which the payload data belongs, such as TCP or UDP. To ensure data integrity, the header checksum field contains a checksum value calculated over the IPv4 header. This value allows the receiving device to verify the integrity of the header and detect any potential errors during transmission. The source IP address field identifies the IP address of the sender or source device that originated the packet. It allows the receiving device to identify the source of the incoming data. The destination IP address field specifies the IP address of the intended recipient or destination device for the packet. It guides the routers along the network path, ensuring the packet reaches the correct destination. And finally, the options field. In addition to the standard header fields, IPv4 also includes an optional field called the options field. This field provides a means to include additional information or specify certain actions to be taken on the packet. It offers flexibility and extensibility in customizing packet behavior based on specific requirements. However, the usage of the options field is relatively rare in modern networks, as most network communication relies on the core set of header fields for efficient routing and delivery. In the IPv4 payload, the only required field is the data field. The data field contains the actual information or payload that is being transmitted over the network. It can vary in content and format depending on the protocol or application using IPv4. For example, if you are sending an email using the Simple Mail Transfer Protocol, SMTP, over IPv4, the data field would contain the email message itself, including the sender, recipient, subject, and the message body. If you are accessing a website using the Hypertext Transfer Protocol, HTTP, the data field would contain the requested web page and its associated content, such as HTML, images, or scripts. The IPv4 address resolution protocol plays a crucial role in modern computer networks by facilitating the mapping of IP addresses to MAC addresses. In a nutshell, ARP allows devices within the same network to communicate with each other using their MAC addresses. It provides a method for resolving an IP address to the corresponding MAC address, ensuring successful data transmission. The ARP protocol operates through a simple request and reply mechanism. When a device wants to communicate with another device on the network but only knows its IP address, it sends out an ARP request. The ARP request is broadcasted to all devices on the local network, asking for the MAC address associated with the given IP address. The device that holds the requested IP address responds with an ARP reply, providing its MAC address to the requesting device. This exchange allows the devices to establish direct communication using their MAC addresses. To optimize network performance and reduce ARP broadcast traffic, devices maintain an ARP cache or ARP table. The ARP cache is a local memory where devices store the mappings of IP addresses to MAC addresses they have recently communicated with. When a device needs to communicate with another device on the network, it first checks its ARP cache. If the mapping is present, it can directly use the MAC address from the cache without sending an ARP request. This caching mechanism speeds up subsequent communications between devices. In addition to the basic functionality, ARP also supports advanced features like gratuitous ARP. Gratuitous ARP is a mechanism where a device sends an ARP announcement containing its own IP and MAC address without receiving a request. It is typically used for network troubleshooting, updating ARP caches of other devices, or detecting IP address conflicts. In the previous video, we explored the concept of public IP addresses within the IPv4 addressing scheme. Now, let's dive into the world of private IP addresses and discover how they function in computer networks. While public IP addresses are used for devices connected to the internet, private IP addresses are designated for local networks, such as home or office networks. These addresses are not routable on the internet and are solely meant for internal communication within the local network. They allow multiple devices within a network to share a single public IP address, reducing the demand for unique public addresses. This is achieved through Network Address Translation, NAT, which allows private IP addresses to be translated into public IP addresses when accessing the internet. The Internet Assigned Numbers Authority has defined specific address ranges reserved for private use. These ranges include 10.0.0.0 to 10.255.255.255.172.16.0.0 to 172.31255.255 and 192.168.0.0 to 192.168.255.255. These private IP address ranges are non-routable on the internet and are meant for local network communication only. Devices within a local network are assigned private IP addresses from these ranges, ensuring unique identification and enabling efficient data transfer between devices. Subnetting is the process of dividing a large network into smaller, more manageable subnetworks. Think of it as creating mini-networks within a bigger network. Why do we do this? Well, it helps improve network performance, enhances security, and allows for efficient utilization of IP addresses. To make subnetting work, subnet masks. The subnet mask determines the network and host portions of an IP address. By applying the subnet mask, we can identify which devices belong to which subnets. In the past, IP addresses were classified into classes, based on their network and host bits. However, this led to inefficient utilization of IP addresses and routing table complications. CIDR Notation solved these problems by introducing a more flexible and efficient approach. If you're interested in diving deeper into CIDR Notation and exploring more advanced concepts, we've got you covered. We have a comprehensive blog post dedicated to CIDR Notation, where you can find detailed explanations and practical examples. The link to the blog post is in the description below. And that brings us to the end of this video. I hope you found this informative and gained a better understanding of the essential concepts we explored. If you enjoyed this video and want to continue expanding your networking knowledge, be sure to check out our blog. We regularly update it with in-depth articles, tutorials, and resources to keep you informed about the latest advancements in the ever-evolving field of networking. To stay up to date with our future videos and never miss a new upload, don't forget to hit that subscribe button and click the notification bell. By subscribing, you become part of our growing community of networking enthusiasts. Thank you for joining me on this learning journey. I appreciate your support and engagement. If you have any questions or suggestions for future video topics, please let me know in the comments below. I value your feedback. Until next time, keep exploring, keep learning, and keep networking. This is Hell's Network, signing off. Take care, and I'll see you in the next video.